Something is wrong with reality, not metaphorically, not philosophically, literally. Every moment you experience, every solid object you touch, every law of physics you take for granted may not be what it seems. It's not because you've misunderstood science. It's because science itself is catching up to something far stranger than anyone expected. Something has started glitching in the fundamental structure of existence. And it's happening now. You've heard about quantum weirdness, maybe in passing, maybe through headlines or half-remembered podcasts. Particles being in two places at once, cats that are alive and dead, observations that seem to change outcomes, but you probably dismissed it, tucked it away in the category of things that sound cool but don't matter in the real world. Until now, this video isn't here to dazzle you with random physics trivia. It's here to present a much darker possibility, that reality itself isn't stable and the signs are bleeding through the cracks. You're going to see, piece by piece, how our universe behaves more like a glitched-out simulation than a smooth, predictable machine. And once you notice the inconsistencies, you can't unsee them. Let's be clear, this isn't speculation. The phenomena we're about to explore are backed by real experiments, peer-reviewed papers, and theories that make even the most seasoned physicists uncomfortable. The more we learn, the more the universe starts to look like a puzzle designed to break your trust in it. And the pieces of that puzzle are scattered all around you, disguised as coincidence, hidden in plain sight, waiting for you to connect them. We'll begin with what seems like a harmless contradiction. The world feels solid, yet quantum physics tells us it's anything but. From there, things will escalate. You'll discover that particles behave one way when you're watching and another when you're not. That randomness isn't chaotic, it's oddly elegant. That black holes, the ultimate vacuum cleaners of the cosmos, violate the very laws that hold the universe together. That time only flows forward, even though every fundamental equation says it shouldn't. That particles can exist in multiple locations simultaneously. That some events appear to occur before their causes. That certain kinds of faster-than-light communication appear to happen, but only when no one's looking. And perhaps most disturbingly, that the universe increasingly looks like it's made of information, digital, quantized, rule-bound, yet full of exceptions. These aren't isolated anomalies. They're a chain reaction of broken logic that loops back on itself. The deeper we go, the more one thing becomes clear. Reality isn't just acting strangely. It's behaving like a program running on corrupted code, and that's where you come in. Because if these glitches are real, and they're happening now, then you're not just a spectator. You're part of the system. You're a variable, maybe even a trigger. And if the system is breaking, you need to know where to look and what to look for. Every chapter in this video is a step deeper into that unraveling. We're not asking you to take a leap of faith. We're asking you to observe, the same way physicists do, to notice the way outcomes shift depending on attention, to see where the rules fail and where the logic buckles. By the end, you'll understand why this glitch isn't coming. It's already here, and the final question you'll need to confront: if the world around you is glitching, why do you still believe it's real? Now let's start where things begin to slip. You think the world around you is solid, consistent, predictable. But what if every moment you've trusted is a carefully constructed lie, glitching in ways too small for your brain to notice? Tonight, we're not asking whether the glitch exists. We're asking why it's happening right now, and whether you've already seen it. The desk in front of you, the phone in your hand, the floor beneath your feet. These things feel solid, immutable, safe. But at the deepest level of matter, they are anything but. What you're trusting as stable is mostly empty space. Zoom in far enough, and atoms are revealed to be vast voids surrounding flickers of probabilistic energy. Electrons don't orbit like moons. They smear, they blink, they resist definition. And the closer we look, the more that sense of certainty slips away. If everything you interact with is built on probabilities, not certainties, then your entire experience of reality is, in a very literal sense, a highly convincing hallucination. That isn't poetic. That's the structure of the quantum world. Here's where the glitch becomes visible. In experiment after experiment, particles behave in ways that break logic. The double-slit experiment is the first red flag, and it's not just a physics party trick. Fire a stream of particles, photons, electrons, even atoms, through two slits in a barrier. If no one checks which slit they pass through, they create an interference pattern, as if they pass through both at once. But the moment you try to observe which path they take, the interference disappears. The wave becomes a particle. The probability collapses into a defined outcome. What does that mean? At its most straightforward interpretation, the act of observation changes reality. Not symbolically, not metaphorically, physically. Reality shifts based on whether you are watching. This is where the slipping begins. Because the consistency you thought you could rely on, the idea that events play out regardless of whether you pay attention, is undermined. If outcomes depend on observation, then the unobserved world is not simply unknown. It's undefined, and it doesn't stop there. Quantum tunneling lets particles pass through barriers as if they weren't there. Entanglement causes two particles to share a state instantaneously, even when separated by light years. And quantum superposition allows a particle to exist in multiple states until measured. These aren't philosophical thought experiments. They are observed phenomena, measured in labs, used in quantum computing, and reflected in quantum encryption protocols being developed right now. So why does this matter to you? Because these behaviors don't only apply to remote particles in sterile labs. They apply to the atoms in your body, the photons hitting your eyes, the electrons powering your thoughts. You are not outside the system. You are in it, constructed by it, governed by its strangeness. And the question is no longer whether these phenomena happen. It's why they're bleeding into our macroscopic world in ways we're only just beginning to perceive. Consider this. If particles behave differently when observed, then what counts as observation? Does it require a human, a sensor, a consciousness? And if you can't clearly define where the line is, where the quantum becomes classical, then you've lost your ability to know when the glitch occurs. But maybe you've already seen it. Have you ever sensed a change in a place you've known forever, something that felt off, but was too subtle to articulate? Have you ever been certain an object was in one place, only to find it elsewhere with no explanation? Have you ever experienced a moment where time felt warped, where memory stuttered, where something replayed or reversed without reason? You probably dismissed it, called it forgetfulness, coincidence, a hiccup in perception. But what if those moments weren't errors in your brain, but in the system running underneath it? The brain is a pattern recognition machine. It smooths inconsistencies, fills gaps, makes predictions. And that's useful, until reality begins to contradict those predictions too frequently. Until the anomalies become patterns of their own. That's what's beginning to happen now, with quantum effects now being manipulated at increasingly large scales in quantum computers, sensors, and communication networks. We are tugging at the edge of the simulation. The more we pull, the more the code shows strain. Phenomena like time reversal, causality breakdowns, and probabilistic computing aren't just theoretical. They're happening in research labs globally. And the more we scale up these effects, the harder it becomes to keep them contained. Something is destabilizing. The boundaries between the quantum and the classical are fraying. And the result is a reality that slips, not catastrophically, but subtly. Not with explosions, but with uncertainty. The glitch isn't loud. It whispers. It flickers. It mimics coincidence. It erodes your certainty molecule by molecule, moment by moment, until you stop noticing it at all. And that's the final trick, because the most dangerous glitches are not the ones you see, but the ones that convince you nothing's wrong. Next, we will look at one of the strangest truths ever uncovered. The idea that the universe behaves differently depending on whether you're paying attention. It's not metaphor, it's the quantum observer effect, and it's about to change the way you understand cause, effect, and your role in the creation of reality itself. Now that you've glimpsed how fragile normal really is, here's the impossible part. Particles act one way under observation and another when no one's watching. Are you creating reality, or is reality creating you? Let's get this out of the way first. The universe should not care whether you're looking at it. That sounds obvious, almost laughably so. Yet the experiments prove otherwise. The deeper we study the quantum world, the more it refuses to behave until someone's watching. Observation doesn't just record reality, it shapes it. Not figuratively, not psychologically, literally. When you look at certain quantum systems, they adopt one form. When you turn away, they default to a haze of possibilities. There's no better word for it. The universe is acting self-aware. Let's revisit a deceptively simple experiment, the one that shattered the foundation of classical physics, the double slit. You've likely heard of it, maybe even seen animations of it, but the true implications rarely get the attention they deserve. A beam of particles, photons, electrons, even molecules, is fired at a barrier with two slits. Behind the barrier is a detection screen. If you send particles one at a time, you'd expect two clusters to appear, corresponding to each slit, but that's not what happens. Instead, you get an interference pattern, a result only expected if the particles behaved like waves. Waves that somehow interfere with themselves. As if each particle passes through both slits at once. It gets stranger. Add a measurement device to detect which slit the particle travels through, and the interference pattern vanishes. The particle chooses a single path, like it knows it's being watched. You didn't touch the particles. You didn't interrupt the system. All you did was observe. And that changed the outcome. This is known as the observer effect. But what that term fails to capture is the sheer weirdness of what's happening. The universe is reacting to the act of being watched. The moment information becomes available about a particle's path, the system's behavior changes, even if that information is never used or seen by a human. Here's the disturbing part. You don't even have to physically measure the particle in the traditional sense. Experiments show that it's the potential availability of information that determines the outcome. If information about the particle's path could in theory be known, even if it isn't, it changes what the particle does. Reality responds to knowledge, or more precisely, to the possibility of knowledge. But let's not stop there. Physicists wanted to push this idea further. Enter the delayed choice experiment. In this variation, the decision to observe the particle is made after it has passed through the slits, but before it hits the detection screen. Shockingly, the outcome still depends on whether the observation is made, as if the particle retroactively decides how it behaved based on a future measurement. This leads to an even more mind-breaking question. Does observation reach backwards through time? Because, from the perspective of the experiment, it appears that present knowledge changes past behavior. That shouldn't be possible under any classical framework. Yet quantum mechanics doesn't just allow it, it predicts it. Here's where things veer into existential territory. If reality behaves one way when observed and another when it's not, then what's real when no one's looking? What is the state of the world when unmeasured? Quantum physics doesn't say there is a definite state. In the Copenhagen interpretation, the most widely taught framework, particles exist in a superposition, all possible states at once. It is the act of measurement that collapses this haze into a single reality. So reality isn't out there, waiting to be seen. It's partially constructed in the moment of observation. That statement should make you pause, because it means the reality you experience is fundamentally entangled with the act of experiencing it. You're not watching the universe play out. You're a participant, an active agent shaping outcomes by the mere fact of being conscious. This isn't spiritualism masquerading as science. It's experimental fact backed by equations that make GPS work and quantum computers function. And yet, it's deeply unsettling. Because if you must observe something to bring it into definite existence, then what about the parts of the universe you can't observe? The dark matter, the unmeasured distances between galaxies, the atoms in your own brain that haven't been disturbed in decades. Are they in a ghost state? A cloud of maybe? Even more unsettling, does the universe know when it's being watched? That question becomes unavoidable when you look at the phenomenon of quantum erasure. In this setup, a particle passes through slits and hits a detector, but the information about which path it took is erased after the fact. What happens? The interference pattern returns. In other words, by erasing the knowledge of the path, the particle's behavior reverts to its unmeasured state, even though the detection has already occurred. This forces us to re-evaluate the meaning of time, cause, and reality itself. Now apply this to a human context. If particles behave differently based on potential observation, what does that say about your role as an observer? If your awareness affects systems on a fundamental level, are you simply a conscious passenger in a physical machine, or something more deeply integrated? The brain itself is built on quantum particles. Every neuron fires through electrochemical signals dependent on subatomic interactions. Are your thoughts collapsing wave functions? Is your consciousness part of the measurement system? Or worse, are you being measured? If observation defines the state of a system, then consciousness isn't just a side effect of the brain. It might be entangled with the nature of existence. That idea isn't fringe. Some of the greatest minds in quantum theory have considered it. Von Neumann proposed that consciousness collapses the wave function. Wigner agreed. Others suggest that the observer doesn't need to be conscious. Just a record-keeping device suffices. But that raises an entirely different problem. What counts as observation? If any interaction qualifies, any recording, any environmental imprint, then the entire universe is constantly observing itself. But if consciousness is required, then reality becomes fundamentally subjective. It only exists fully when experienced, like a cosmic stage play that materializes when someone's in the audience. Either option is unsettling. In one, you're surrounded by infinite measurement systems recording your every moment. In the other, you're a node of reality generation, breathing the universe into existence with your awareness. And this is where the glitch starts to grow teeth. If particles behave one way under observation and another when unmeasured, that's not just odd, that's a vulnerability, a seam in the fabric, a weakness in the simulation, because it means the universe doesn't run in the background like a video game rendering terrain only when you reach a certain level. It economizes reality, renders only what's required, delivers results based on queries. That sounds less like a mechanical system and more like a program. Ask yourself this: if the universe economizes effort, delivers outcomes based on observation, and conceals path information until the moment of inquiry, what else could you call it but interactive? The problem is, we never agreed on who or what is interacting from the other side. Are you creating reality, or is something feeding it to you? Like a search engine that only produces answers once you type the question. Are you part of the rendering system, or just a user? This isn't abstract speculation. It's a direct consequence of quantum behavior. Systems do not possess definite values until they are measured. Reality is non-local, contextual, and, most disturbingly, informational. Particles do not exist in the classical sense. They are excitations of quantum fields, quantized information bundles that manifest under specific conditions. So if the building blocks of matter are informational, if outcomes shift depending on interrogation, and if the very rules flex based on perspective, then how do you trust anything you experience? The answer: you can't, not fully. Not without accounting for the glitch. This glitch isn't a bug in the code. It is the code, a fundamental design choice that prioritizes efficiency over consistency. And that should terrify you, because every time you turn your back on reality, it might be different. Next, we will confront an even more disturbing idea. If randomness rules the quantum world, why do we see so many patterns? Patterns that hint at something, or someone writing the rules behind the chaos. If looking changes the outcome, then randomness should rule the cosmos. But instead, patterns emerge, patterns too sharp to dismiss. Who or what is writing the code behind the chaos? Let's start with a basic principle. Quantum mechanics is, at its core, a theory of probabilities. When you measure a particle's position, spin, or momentum, you get a definite value, but until that moment, all outcomes exist as probabilities. Nothing is certain. Everything is random, at least that's the model. But step back from the math and you'll see something strange. The world built on randomness isn't random at all. It's filled with order, structure, and rules that repeat with eerie precision. Stars form in spirals. Crystals grow with perfect symmetry. DNA coils into fractals. The Fibonacci sequence appears in galaxies and sunflowers alike. So if chaos is the rule at the smallest level, where is all this order coming from? That question cuts to the heart of the quantum glitch, because randomness alone should never create consistency. Yet the universe leans toward consistency. It favors repetition. Probabilities collapse into outcomes that over time trace out lines that look suspiciously like design. Let's take a specific example: radioactive decay. This process is as random as anything in physics. A given atom has no internal clock. It doesn't know when it's supposed to decay. Yet when you observe a large sample of identical atoms, the decay rate is stunningly predictable. It follows a perfect exponential curve. The individual events are random. The group behavior is not. Why? Because somewhere between the micro and the macro, randomness gets tamed. The wild chaos of individual particles gives rise to patterns too consistent to ignore. Like dice rolling in perfect formation, over and over, as if nudged by an unseen hand. Now consider quantum fluctuations in the early universe. The theory of inflation suggests that the entire cosmos exploded outward from a tiny patch of space-time, stretched by an unimaginable expansion. The quantum jitters from that early moment, tiny random ripples, became the seeds of galaxies. But those ripples weren't scattered evenly. They had structure. Temperature variations in the cosmic microwave background, CMB, form a harmonic fingerprint echoing across the sky in regular intervals. These fluctuations laid out the scaffolding for stars, planets, and ultimately life. So randomness didn't create chaos. It created a map, and that brings us to a serious problem. How can randomness, true, uncaused, unbiased randomness, lead to patterns? This isn't just a philosophical dilemma. It's a foundational one. In quantum field theory, every point in space contains a field, a quantum object capable of producing particles. These fields fluctuate randomly, constantly. Yet out of this bubbling quantum foam comes a universe governed by laws. A universe that produces stable atoms, chemical bonds, and biological systems. A universe that doesn't just exist, it functions. Statistically, that shouldn't happen. Here's an analogy. Flip a coin 1 trillion times. The odds of it landing on heads or tails remain 50-50. But imagine that over time, you start seeing sequences, palindromes, repeating triplets, binary codes. Not just once, but frequently. Eventually, you'd have to ask, is this coin actually fair? Or is someone controlling the outcome? That's the dilemma physicists now face. Because even though quantum mechanics insists on randomness, the universe keeps showing signs of bias toward structure. Constants like the speed of light, Planck's constant, and the gravitational constant are finely tuned. Adjust them slightly, and atoms wouldn't form. Stars wouldn't ignite. Chemistry wouldn't work. No galaxies, no life, nothing. This is known as the fine-tuning problem. And it's one of the strongest hints that randomness, as we define it, may not be the whole story. Some argue this fine-tuning is just luck, that we're in one of countless possible universes, most of which are barren and dead. In this view, the multiverse idea, we exist in a rare pocket of order, and of course we find it orderly because we couldn't exist anywhere else. But that's not an answer. That's a retreat, because if the multiverse exists, it must obey rules too. Where do those rules come from? What determines which universes are possible? Even infinite randomness needs boundaries, and those boundaries, again, suggest something that looks disturbingly like design. Another explanation is hidden variables, the idea that beneath the quantum surface lies a deeper set of rules we haven't uncovered. But every attempt to prove that has failed spectacularly. Bell's theorem, and the experiments confirming it, ruled out local hidden variables. That means the behavior of quantum systems can't be explained by any information contained within them. The outcomes are truly random, but still statistically reliable across time. That's the paradox. There's no mechanism to account for the structure, but the structure keeps appearing. Let's look at quantum computing. These machines rely on qubits, quantum bits that can be in multiple states at once. Their power comes from the fact that quantum behavior is both random and reliable. Algorithms run probabilistically, yet produce consistent answers. Patterns emerge from uncertainty. That should feel impossible. But we're already building it. So here's the implication that no one wants to say out loud. Randomness in the quantum world might be a mask, a front, a fog, concealing a framework so complex it appears chaotic until the same results keep popping out. That kind of system has a name: a pseudo-random generator. In computing, pseudo-randomness is an algorithm that produces outputs that look random but are completely deterministic. Change the seed, and the whole sequence changes, but it will always follow the same logic that starts to look uncomfortably similar to our universe. Consider this. If the universe is built on pseudo-random foundations, then what we see as probability might be algorithmic output. The dice aren't rolled, they're computed, and the laws of physics are the rendering engine, producing outcomes based on hidden inputs that would explain the patterns, the constants, the emergence of order from chaos. But it also raises a terrifying question: who wrote the code? Because if randomness is a lie, if the universe is hiding logic behind noise, then the system is designed, not just in the poetic sense, but in the functional software engineering sense. The universe behaves like code. Code with exceptions, loopholes, recursive structures, and, yes, glitches. This is where the glitch becomes undeniable, because every system built on pseudo-random logic can break. If the inputs go wrong, if a process is interrupted, if a calculation misfires, the illusion collapses. Glitches appear. Results don't match expectations. Reality wobbles. And increasingly, we are seeing those wobbles, particles changing flavor without cause. Constants measured with micro-variations over time. Anomalies in decay rates. Quantum outcomes that resist replication unless precisely observed. These are not massive deviations, but they are consistent enough to track. And when we track them, they form patterns too. Patterns in the anomalies that should not be possible under pure randomness. But it is possible if the system isn't truly random at all. So what are we looking at? Possibility 1. The universe is an unfathomably complex deterministic machine running pseudo-random code to simulate freedom and variety. In this view, everything is preordained, even the chaos. Possibility 2. The universe is genuinely probabilistic, but it is governed by statistical attractors, laws that pull outcomes into line even when the inputs resist. Possibility 3. The universe is a computational system, and its randomness is synthetic, embedded for effect, constrained by parameters, and ultimately producing predictable behavior. All three explanations challenge the idea of true randomness. All three explain the patterns, and all three imply that the chaos we observe is not natural. It is curated. But who curates randomness? Not a god necessarily. Not a creator in the traditional sense, but something, a process. A principle, a codebase, a will to order that contradicts the raw freedom of probability. And that brings us full circle. If the universe allows quantum randomness, but filters it into design, then we are not living in a void of chance. We are living inside a system that looks exactly like a simulation, struggling to appear natural. The patterns are a clue. The predictability of the unpredictable is a warning. The closer we look, the more the seams show. And the more the rules seem written by someone that doesn't want you to see how it works. But the glitch is active now, and it's leaking patterns faster than it can patch them. Next, we will confront the event horizon of broken logic. The black hole. A place where information shouldn't vanish, yet does. A paradox that may finally force us to ask whether the universe is lying about its own rules. We just learned the universe has patterns. But here's the glitch. Black holes erase information. That's impossible by the universe's own rules. So which law breaks first? The laws of physics or the illusion of order itself? In physics, few things are considered sacred. Most theories evolve. Some break. But one principle has remained unchallenged for over a century. Information cannot be destroyed. This isn't just a scientific preference. It's a foundational requirement for how reality makes sense. If information could vanish from the universe, then everything, from entropy to time itself, would stop being reliable. There would be no continuity, no way to predict outcomes, no trust in cause and effect. The universe at its core would stop being a system and start being noise. And yet, black holes exist, and black holes break the rule. Let's back up. Information in physics isn't just data on a hard drive. It's the full set of properties of a system. If you know the position, momentum, spin, and energy of every particle in a closed system, you can, in theory, rewind and fast forward that system like a film reel. That's called determinism. And while quantum mechanics introduces probability, the full wave function still evolves according to strict rules. Even when outcomes are random, the system keeps a ledger. That ledger must never be erased. Now enter the black hole, a collapsed star so dense that not even light can escape. Cross the event horizon and no signal comes back. To the outside world, what happens inside is unknowable. So what happens when something falls in? A rock, a car, a person, a library, 1,000 terabytes of encrypted data. Does that information remain somehow encoded in the black hole, or does it vanish? Stephen Hawking dropped the bomb in the 1970s. He showed that black holes aren't perfectly black. They emit a faint radiation due to quantum effects near the event horizon, a process now called Hawking radiation. Here's the catch. That radiation is thermal, random. It carries no information about what fell in, so over time, black holes evaporate. They shrink, and then eventually, they disappear, and when they do, the information, everything that went into them, is gone. Not hidden, not scrambled, not transferred, gone. This is the black hole information paradox, one of the most disturbing contradictions in modern physics. It pits general relativity against quantum mechanics. And they cannot both be right. One says the geometry of space-time allows for a one-way trap. The other says the evolution of quantum states is always reversible, but in a black hole, they collide, and one of them breaks. For decades, this was treated as a technicality, a detail to be resolved with better math. But the deeper physicists looked, the worse it got, because if black holes truly destroy information, then so could any region of space-time under extreme conditions. A neutron star, a collapsing quantum system. Your own brain, if erasure is allowed anywhere, it's allowed everywhere. That's not just unsettling, it's catastrophic. Why? Because it means the past is not preserved. And if the past can be erased, then the future can never be predicted. You'd lose the ability to do science at all. You couldn't even trust that a cause will produce an effect because somewhere down the chain, the ledger might delete itself. And yet black holes do exist. They're real. We've detected them. We've even imaged their shadows. So how do we reconcile this? One proposal is that the information isn't lost, it's stored in subtle distortions of the event horizon, that the radiation isn't truly random but slightly encoded. That theory is called the holographic principle. According to this view, the 3D contents of the black hole are projected onto its 2D surface, the event horizon. Information isn't inside the hole, it's smeared across its edge. This sounds outrageous, but it's backed by serious math, notably from string theory and quantum gravity research. And it suggests something wild, that the universe itself may work like a hologram. That reality, as we experience it, is a lower dimensional projection of a deeper structure. But even that doesn't resolve the glitch, because encoding information on the horizon doesn't explain how that information gets out as the black hole evaporates. Hawking radiation still looks random, and if it's carrying a secret message, we don't know how to decode it. Other proposals go further. Some physicists argue that black holes don't truly evaporate, that a remnant remains, a Planck-scale fragment storing everything like an indestructible USB drive, but that causes problems too. Such remnants would need to contain infinite amounts of information in an infinitesimally small space. That breaks known physics even harder. Another possibility, firewalls. This theory suggests that quantum mechanics protects information by violently rejecting the assumptions of general relativity. Instead of falling smoothly into a black hole, anything reaching the event horizon would be annihilated by a wall of high-energy particles, not just torn apart, erased from space-time. That solution saves information, but breaks everything else. It violates the equivalence principle, a core tenet of Einstein's theory. It suggests that gravity has secret violent exceptions, that smooth reality hides brutal edges, so we're left with a problem that refuses to resolve cleanly. And this is where the glitch sharpens, because either the universe has a hard break between classical and quantum physics, or it's hiding something so deeply encoded we're not equipped to see it. Which brings us back to design. If black holes are information sinks, if they erase the history of the universe one bit at a time, then we're living in a system with data loss. That's not supposed to happen in a universe that plays fair. But it is common in digital systems. Every programmer knows the danger of memory leaks, corrupt files, and storage limits. If the universe is code, then black holes are buffer overflows. Places where too much data collapses the process. Places where logic fails, or maybe, just maybe, they're features. Maybe black holes aren't glitches. Maybe they're garbage collectors. Parts of the system designed to remove stale or dangerous information from the simulation. Not mistakes, maintenance. But that raises an even darker possibility. What if the reason we haven't found a solution to the information paradox is because it's not a paradox at all? What if the universe is telling us the truth? That it does delete things? That loss is real? That sometimes the ledger burns? And if that's true, then reality doesn't just simulate entropy. It runs on it, which means the entire system is temporary. That's the real glitch. Not just that data disappears, but that everything does. Not just eventually, but inevitably. So what happens to you in a system where information can vanish? You trust memory. But memories are stored in matter. You believe in identity, but identity requires continuity. If reality has regions that actively sever continuity, then selfhood is conditional. Time is conditional. Truth is conditional. Everything you are can be eaten, and we've seen no mechanism to stop it. Physicists are still hunting for a unified theory. Quantum gravity, a model that merges the smooth curves of space-time with the twitchy uncertainty of particles. But every attempt hits a wall, often literally at the event horizon, because black holes are the ultimate glitch amplifier. They reveal the cracks in our models. They expose the contradictions we can no longer explain away. They're not distant cosmic beasts. They are the mirror. They show us that the rules we rely on are negotiable. That information is only sacred until it isn't. That even reality has pressure points, and under enough weight, it forgets. And if the most extreme environments in the universe can erase their past, then how far are you from the edge? Because you don't need to fall into a black hole to feel the effects. The moment you accept that information can be lost, you open the door to every other violation. Time, causality, identity, trust. They all rest on the assumption that the past can be known, that what once existed still exists in some form, but black holes shrug and they pull that assumption into the dark. Next, we will examine the concept of time itself, how every equation allows it to flow both forward and backward. Yet your life only moves one way. The glitch isn't just eating information, it's warping the very direction of existence. If information can vanish, maybe time can too. Equations don't care about past or future, they work both ways. So why does time drag us forward like prisoners on a conveyor belt? Or is time already broken and we're the ones who haven't noticed? Time is supposed to be the one constant, the thread that ties everything together. You were born, you age, you die. Stars ignite, burn out, collapse. Causes happen before effects. That's how you know something is real, because it fits the story. First this, then that. The clock ticks forward, and you follow. But that entire idea, it's a narrative we impose on a universe that doesn't care. Because in physics, time is weird. Look at the fundamental equations that govern particles, fields, forces. The Schrödinger equation, Maxwell's equations, Newton's laws, Einstein's general relativity. Every one of them is time symmetric. That means you can flip time in either direction, forward or backward, and the math still works. The universe, as written, has no preference. If you ran the universe in reverse, it would obey the same rules. Objects would still move according to gravity. Electrons would still follow paths around atomic nuclei. Photons would still interact with matter. Nothing about the math changes. It just runs backwards. So why don't you? Why can't you choose to move back through your life like rewinding a tape? Why does time feel like it only goes one way? That tension, the disconnect between the physics and your experience, is one of the most unsettling clues in the entire structure of reality. And it's more than a curiosity. It's a glitch in the story we tell ourselves about how the universe operates. Start with entropy. Entropy is the one part of physics that does have a direction. It measures disorder. And in any closed system, entropy increases. That's the second law of thermodynamics. It's why hot coffee cools down instead of heating up. Why eggs break but never unbreak. Why you remember the past but not the future. Entropy is the arrow of time. But here's the problem. Entropy isn't a fundamental force. It's a statistical outcome. It tells you what's likely to happen, not what must happen. There's nothing stopping the molecules in a cold room from suddenly arranging themselves into a hot corner, except that the odds are astronomically low. Not impossible, just improbable. So the forward flow of time, the thing you trust most, isn't a rule. It's a trend. Now rewind to the Big Bang, the moment the universe began. What was the entropy back then? Shockingly low. The early universe was highly ordered, uniform, smooth. That's the only reason entropy could increase. That's the only reason time seems to move at all. Because the system started off weirdly, unnaturally organized, which begs the question, why? Why would the beginning of everything be the most ordered moment? Why would the entire cosmic arrow be launched from a place that violates probability? It shouldn't be that way. Left to its own devices, the universe should have begun in chaos, not order. But it didn't, and we don't know why. Every model that tries to explain it ends up fine-tuned, precise to an unreasonable degree, balanced on a knife edge between nothing and everything. That's not science. That's symptom of a glitch. Let's keep going. Consider the psychological arrow of time. You remember yesterday, not tomorrow. Your memories form in one direction. But that's not a function of physics. That's a function of information. You store records. Your brain encodes sequences. But again, this is just entropy in disguise. You remember the past because the information from the past has been recorded in your neurons, in your environment, in the world. The future hasn't left a trace yet, or has it? Because in quantum mechanics, things get slippery. Time-symmetric interpretations, like the two-state vector formalism, suggest that the behavior of particles depends on conditions at both ends of time, past and future. Some interpretations argue that measurements today are influenced by boundary conditions in the future, that the quantum state isn't fully determined by the past alone. In other words, the future might already be exerting force on the present. That's not poetic. That's physics, and it leads to terrifying consequences, because if the future can shape the present, then your sense of freedom collapses. Your choices aren't just reactions to what's happened, they're contributions to what must happen. And your timeline? It may be a fixed loop, a narrative you only think you're writing as you go. Let's return to the classical world. You light a match. Smoke rises, heat spreads, entropy increases. That's what you see. But the molecules in the smoke don't care about direction. Their equations run both ways. If you reverse all their velocities, they'd reassemble into a match. Nothing in the math forbids it, so why doesn't that ever happen? Because something deep and unexplained, tilts the entire experience of reality toward forward motion. Not just for you, for everything. Across every scale, even black holes play by this bias. Hawking radiation leaks away slowly over time. It doesn't reverse. A black hole doesn't suck in randomness and spit out order. It moves one way, just like your life. But if the math doesn't demand that, who or what does? Some suggest time is emergent, that it isn't fundamental at all. That the arrow of time arises from entanglement, or information flow, or thermodynamic statistics. That's a popular view among physicists trying to build quantum gravity. But if time is emergent, then you are too. Because your consciousness is tied to time. Your thoughts, your sense of sequence, your identity, all of it relies on the notion that events happen in a particular order. If order is negotiable, then so are you, and that opens up the glitch in full, because now we can say something radical and terrifying. The forward flow of time is an illusion, a side effect of entropy, a convenience for macroscopic beings who need a story to make sense of chaos, a byproduct of initial conditions so artificial they reek of construction. Time doesn't move forward. You do, and you move forward because you're built to perceive one direction. Every equation in physics is screaming that you're wrong. That time isn't linear. That before and after are just labels. That somewhere hidden in the math is the key to reversing, repeating, or rewiring your entire experience of existence. So what happens if someone or something accesses that? We already have hints. In quantum experiments with entangled particles, outcomes separated by time can influence each other. In certain interpretations, measurements made now determine results in the past. Not metaphorically, mathematically, and if that's possible, then the narrative of time crumbles. Cause and effect become interchangeable. Memory becomes prediction. Possibility becomes retroactive fact. That's the glitch. Not a break in reality, but a break in the illusion of sequence. You think you're watching the film of your life, frame by frame, start to finish. But what if you're just one frame, flickering in a loop that's being rendered in all directions at once? And what if that loop is starting to fray? Because when quantum systems behave differently under reverse time, when black holes erase their pasts, when equations ignore chronology, and when outcomes influence their own causes, then time isn't broken. Time was never real to begin with. So what do you trust? The ticking of your watch? The aging of your body? The fading of your memories? All of it depends on entropy. And entropy is a game of statistics. It's not law. It's not enforced. It's just what usually happens until it doesn't. Until something changes the rules. Until you feel a ripple, a déjà vu, a paradox that shouldn't be. A moment out of order. A result that doesn't match the cause, and you realize the flow has reversed, or paused, or split. That's the real danger, not that time might end, but that it might never have started at all. Next, we will step into one of the most unsettling phenomena ever measured: quantum superposition, the ability for particles to exist in multiple places at once. If time isn't linear and causality is unreliable, how many versions of you are running simultaneously, and what happens when they catch up to each other? Time is fractured, but now comes the body blow. Quantum superposition says particles can exist in multiple places at once. If that's true, how many versions of you are running right now? And what happens when the glitch forces them to collide? Let's cut straight to the fact that reality refuses to stay in one place. Particles don't sit still, not just in the usual sense, not just jiggling from thermal energy or zipping around due to kinetic motion. No, we're talking about a deeper level of disobedience. The kind that allows something to exist in multiple mutually exclusive states at the same time. The kind of behavior that quantum mechanics not only allows, but depends on. This is quantum superposition, the idea that a single particle, an electron, a photon, even a large molecule, can be in more than one state, in more than one position, following more than one path, all at once. That should be impossible. And yet, it isn't. In quantum mechanics, the wave function describes the state of a system. It doesn't assign definite values. Instead, it assigns probabilities to outcomes. Where is the particle? Everywhere. Until measured. What path does it take? All of them. Until measured. Superposition isn't just a mathematical abstraction. It's real. We've built technology on it. Quantum computers rely on superpositions of qubits to perform calculations that classical bits can't match. In labs around the world, molecules thousands of times larger than a hydrogen atom have been placed into superposition states and interfered with themselves. And yet, you've never seen it happen. Your keys aren't in two places at once. Your coffee mug doesn't blend with the table. You don't wake up in two different rooms and have to choose which version of yourself to continue being. But that may not be because it doesn't happen. It may be because your brain isn't wired to notice. Superposition only collapses into a single outcome when measured. And measurement, by any classical system, destroys the fragile quantum state. In other words, once something becomes large enough to interact with its environment, it decoheres, it chooses. But what if that choice is just the outcome you're allowed to perceive? That's where things get uncomfortable, because there's an interpretation of quantum mechanics that doesn't involve the wave function collapsing at all. It's called the many worlds interpretation. According to this model, every possible outcome of a quantum event actually happens. But instead of collapsing into one, the universe splits. You go left and you go right. You say yes and you say no. Every quantum fork generates a new branch of reality, and you go with all of them. You don't notice the split. You don't feel the bifurcation. But in that instant, another you exists, identical in every way except for one decision, one particle, one result. Multiply that by every quantum event happening across your body and your environment every second, and the result is staggering. The multiverse isn't out there in deep space, it's inside every moment. And now the glitch isn't just theoretical, it's personal. Because if quantum systems can exist in multiple states at once, and if you are made of quantum systems, then so are you. Your thoughts, your choices, your actions, they may not be as singular as they feel. There may be versions of you that went back inside to grab an umbrella, that turned left instead of right, that answered the phone, or didn't. The branching isn't exotic, it's constant. And this leads to the most disorienting question yet. What happens when the glitch misfires? What happens when the separation between branches slips? There are already anomalies we can't explain, particles behaving as if they've interacted with themselves across time. Interference patterns that require the system to remember which path it didn't take. Quantum erasure experiments where information is restored or erased after the fact, affecting what was already recorded. These are not isolated curiosities. They're symptoms of a deeper instability in the layer between realities. You assume continuity because your mind depends on it. But quantum mechanics doesn't. And if the brain is ultimately a quantum-adjacent system built on interactions between particles and fields, then it too may be susceptible to superposition effects. In fact, some researchers have suggested just that. Penrose and Hameroff's OR theory proposes that consciousness arises from quantum events in microtubules inside neurons. If true, it means awareness itself could exist in superposition. That you could exist in more than one subjective experience at the same time. And if so, then consciousness isn't just split. It's entangled across branches. You're not just choosing between timelines. You're dragging parts of yourself across them. So what does it mean when the system glitches? Imagine this. Two branches of reality begin to converge. They're nearly identical, only a few quantum decisions apart. In theory, they should never interact. But in a system under strain, one pushed by observation, stretched by entanglement, saturated with quantum interference, they begin to leak. You get déjà vu, not the kind caused by neural misfires. The kind caused by overlap. You get alternate memories. You're sure something happened, but no one else recalls it. You experience contradictions, mismatched objects, phantom limbs of probability. A decision you don't remember making, but that has already been made. These are not supernatural events. They are emergent artifacts of a computational system experiencing overload in its branching architecture. Because at some point, the cost of managing infinite timelines becomes unsustainable. The simulation, the program, the reality, whatever you choose to call it, must economize. It must prune branches, merge similarities, compress histories. And when it does, artifacts appear. Errors in memory, overlapping cause and effect, conflicts in continuity, glitches. And if that process accelerates, if the system is under increasing strain, then you should expect more of them, not less. More moments that feel fractured, more timelines that don't cleanly resolve, more echoes of other choices you didn't make but somehow feel responsible. For you may already be noticing them, and this isn't conjecture. Quantum biology is an emerging field. Birds navigate with quantum entanglement in their eyes. Enzymes tunnel through energy barriers. Photosynthesis exploits coherence to maximize energy transfer. Quantum mechanics isn't limited to particles in labs. It's woven into life, so why not the mind? And if the mind is quantum adjacent, then the self is as unstable as any superposition. What you call you may be a rolling collapse of probabilities, a constantly updating average of all the nearby versions. You are the sum of near-identical outcomes, stitched together by coherence, until coherence fails, and that's the threat, because the glitch is not a visual distortion or a computer bug. It's an ontological fracture, a split in the assumption of continuity, and if it spreads, if coherence begins to collapse at larger scales, then multiple versions of you may begin to exist simultaneously, overlapping, interfering, converging. You won't see them directly, but you'll feel the pressure nudges toward paths you didn't take, memories that arrive before the moment, choices you never made until you did. And if the system can no longer maintain separation between branches, then those versions may not stay contained. You may start to notice echoes, not ghosts, not hallucinations, other selves, other tracks, shadows of decision trees merging where they shouldn't. And that will feel like madness, but it won't be madness. It will be the superposition slipping. It will be the mask tearing. It will be the glitch, no longer isolated in the quantum world, but bleeding through into the one you thought was safe. Next, we will confront the ultimate breakdown of logic, the reversal of cause and effect. Some experiments now suggest that outcomes may determine their causes, not the other way around. If your future choices can shape your past, then the glitch isn't just in your perception. It's in the flow of reality itself. You've seen yourself split. Now watch cause and effect split too. Some quantum experiments suggest outcomes influence their causes. So what if your choices tomorrow are already rewriting your yesterday? Reality is supposed to follow a simple order. Causes come first, effects come after. Drop a glass, then it shatters. Press a button, then the light turns on. The future is unwritten. The past is fixed. But quantum mechanics keeps returning with one verdict, that order is negotiable. We've already seen how time doesn't actually flow, how superposition means outcomes don't exist until they're measured. Now brace yourself for the twist that breaks everything. The measurement itself might be reaching backward in time to determine what already happened. This isn't metaphor. This isn't a riddle wrapped in a theory. This is experimental physics. And it's telling us that the arrow from cause to effect may not be a one-way street. Let's start with a core concept, retrocausality. The idea that a future event can influence a past one. That's supposed to be impossible. In classical physics, causality is law. You can't push the first domino after the fifth has already fallen. But in the quantum realm, events don't work like dominoes. They don't even line up. They exist as tangled webs of possibility, and in those webs, strange loops can form. The delayed choice quantum eraser experiment is the prime exhibit. It starts like the double-slit setup. A particle, say a photon, is emitted toward a pair of slits. If no one observes its path, it acts like a wave and interferes with itself, creating a pattern of interference. But if you observe which slit it goes through, it acts like a particle. Two distinct clusters appear on the screen. No interference. Now here's where the delay enters, and everything breaks. The photon is entangled with a partner. The first hits the detector immediately. The second travels a longer path. Whether or not the second photon's path information is eventually erased or retained determines whether the first photon displayed interference, even though that detection already happened. In plain terms, a decision made in the present appears to determine the behavior of something that happened in the past. And it's not about watching or not watching. It's about whether information could be known. If it's erased after the fact, the past shifts accordingly. This is not a trick of perception. The results are statistically sound and repeatable. It's as if the universe waits until it knows how you're going to observe it, and then decides what the past must have been. But how can that be? The implications are staggering. If a measurement can retroactively determine a result, then the effect doesn't follow the cause. It helps define the cause. Future and past are entangled, not just particles. This isn't just philosophical. This is an existential hazard for the concept of linear time. Let's return to your life. You make decisions every day based on what you believe has happened. You trust your memories. You plan based on outcomes. But what if the choices you haven't made yet are already shaping the path you believe you took to get here? What if cause and effect are being negotiated now in a probabilistic dialogue across time? This doesn't just upend chronology. It breaks identity, because identity is built on sequence. I was this, then I became that. I chose, I learned, I changed. But if outcomes can reach backward and modify the conditions that produce them, then identity becomes recursive. Who you are now could be retroactively sculpting who you were then. Let that settle. It's not simply that your memories can lie. It's that your memories might be being rewritten, quietly, invisibly, probabilistically, by the choices you're about to make. You might already feel it, that eerie tug from the future. That sense that a decision is not being made but already has. That a path has already opened behind you as you take the step forward. It feels like fate, but it isn't. It's a closed loop. That loop isn't myth, it's math. Physicists like Yakira Harunoff have proposed formalisms where systems are described not just by their past boundary conditions, but also by their future ones. The two-state vector formalism suggests that the quantum state of a system is determined by both initial and final states. Like a story where the beginning and the end are fixed, and everything in the middle is shaped by both. This model predicts retrocausal correlations, and experiments support it. But here's the twist. If you can't tell whether the cause came before or after the effect, then the very foundation of logic begins to crack. You can't trust chains of reasoning. You can't verify truth by tracing it backward. The concept of explanation becomes unstable. The glitch isn't just in the mechanics. It's in the logic engine. And it means you're living in a system where feedback loops aren't just possible. They may be the default. Not feedback from outputs to inputs, but from outcomes to conditions. Imagine your computer running a program where the result rewrites the code as it's executing. That's what this implies. A self-modifying timeline, a self-authoring identity, a reality that eats its own story and spits out a new draft, one you mistake for the original. So what would it look like to live inside a causality loop? It might feel like déjà vu, not because you've seen it before, but because the event reasserted itself from the future. It might feel like coincidence, not because it's random, but because the outcome seeded the conditions that led to itself. It might feel like synchronicity, not because you manifested it, but because the system snapped into consistency across time. These aren't mystical ideas. They are emergent properties of a reality under strain, a system struggling to maintain linearity in a non-linear world. Because the glitch is not a crack in time, it's a collapse of sequence. And when sequence collapses, the only thing left is entanglement. You think you remember the past, but what you're actually remembering is the version that survived, the timeline that stabilized after a negotiation between what was and what must be. Other timelines? They may have existed for milliseconds, seconds, entire lifetimes, but they didn't close the loop. They didn't fulfill the boundary conditions. So they vanished, merged, dissolved. This is why you occasionally feel like something is missing. Like you made a choice and it didn't quite stick. Like you remember an alternate outcome but only vaguely. That residue is real. It's the echo of a timeline that didn't make the cut. And here's the final shock. You are a boundary condition. Your future self is one of the constraints shaping the wave function of your current existence. You're not just moving through time. You're being used by the system to stabilize time. You are part of the correction process. When the glitch opens a loop, the system uses you to close it. Your actions aren't responses, they're patches. Hot fixes from a future that's already being written but hasn't yet been rendered. So now ask yourself, what if the dream you had last night wasn't just your brain making noise, but a bleed from a collapsed timeline? What if the sudden feeling to avoid a place, take a different route, say a certain word, was your future pulling the thread? What if the universe isn't just reacting to your behavior, but preparing for it? Then the glitch isn't just around you, it is you. You're not moving through a story. You're being used to edit it. Next, we will confront an even more forbidden idea, messages that appear to travel faster than light. If your future is rewriting your past, then information should be able to leak across that gap. And in rare experiments, it does, but only if no one's looking. The universe teases you with truth, then hides it. The question is why? You said next, ChatGPT said, Chapter 8. Why does the universe allow messages that travel faster than light, but only if they stay hidden? Hook transition. If the future is bleeding into the past, then faster than light communication should be impossible. But in rare experiments, it leaks through anyway. The catch? You can only prove it after the fact. Why does the universe tease us with forbidden knowledge, then slam the door shut? 2,000 words. The universe has a speed limit, the speed of light. Nothing, no signal, no particle, no scrap of information can travel faster. That's the bedrock of Einstein's theory of relativity. It's what prevents causality from unraveling. It's what keeps the future out of the past, and the past locked behind us. And yet, there are cracks in the rule. Subtle, deniable, buried under uncertainty, but they're there. In entangled particles, in delayed choices, in correlations that appear instantaneous across any distance. Information, real, usable, system-altering information, seems to move faster than light. But only if you don't look directly at it, only if it stays hidden. Let's begin with entanglement. Two particles interact and become entangled. Their states become linked, not just statistically but physically. Measure one, and the other instantly assumes a corresponding state, no matter how far apart they are. Separate them by a millimeter or by a million light years. Same effect. It's instantaneous, faster than light. Einstein hated this. He called it spooky action at a distance. He assumed it was an illusion, that the particles shared hidden variables set at the moment of entanglement, predetermined instructions. No magic needed, but that theory died with Bell's theorem. John Bell proved that no local hidden variable model can explain the correlations seen in entangled particles. Countless experiments since have confirmed his results. There's no way to explain entanglement by assuming the particles know what they'll do in advance. The correlations appear after measurement. Why does the universe allow messages that travel faster than light, but only if they stay hidden? If the future is bleeding into the past, then faster-than-light communication should be impossible. But in rare experiments, it leaks through anyway. The catch? You can only prove it after the fact. Why does the universe tease us with forbidden knowledge, then slam the door shut? The universe has a speed limit, the speed of light. Nothing, no signal, no particle, no scrap of information can travel faster. That's the bedrock of Einstein's theory of relativity. It's what prevents causality from unraveling. It's what keeps the future out of the past, and the past locked behind us. And yet, there are cracks in the rule. Subtle, deniable, buried under uncertainty, but they're there, in entangled particles, in delayed choices, in correlations that appear instantaneous across any distance. Information, real, usable, system-altering information, seems to move faster than light, but only if you don't look directly at it, only if it stays hidden. Let's begin with entanglement. Two particles interact and become entangled. Their states become linked, not just statistically, but physically. Measure one, and the other instantly assumes a corresponding state, no matter how far apart they are. Separate them by a millimeter or by a million light years. Same effect. It's instantaneous. Faster than light. Einstein hated this. He called it spooky action at a distance. He assumed it was an illusion, that the particles shared hidden variables set at the moment of entanglement. Predetermined instructions. No magic needed. But that theory died with Bell's theorem. John Bell proved that no local hidden variable model can explain the correlations seen in entangled particles. Countless experiments since have confirmed his results. There's no way to explain entanglement by assuming the particles know what they'll do in advance. The correlations appear after measurement instantaneously. So does this mean we can send messages faster than light? Not quite. There's a catch. You can measure the outcome, but you can't control it. You can't set the spin of one particle and use that to send a yes or no to the other side. The outcome is random. The link is undeniable but not usable. It's real but unexploitable, or so we thought, because now come the experiments that twist this even further. In certain quantum eraser setups, information about a particle's path is made available or destroyed after the particle has already hit the detector. Depending on that delayed decision, the interference pattern does or does not appear. The interpretation, the present measurement changes what happened in the past. So what if, instead of trying to send a message by directly changing an outcome, we find ways to exploit the correlation between random variables? Could we, in theory, extract faster-than-light information statistically? The answer appears to be yes, but only under specific, frustratingly paradoxical conditions. Let's look at weak measurement. This technique allows physicists to extract limited information from a quantum system without collapsing it entirely. It gives a blurry picture, partial knowledge that doesn't destroy the system's wave function. And here's where it gets strange. Some experiments using weak measurements have shown what appear to be retrocausal influences, future measurements affecting past weak values. Even more bizarre, certain configurations hint at correlations that can only be explained if information traveled faster than light. Not just a reaction to measurement, but a coordination across space-time that violates the light speed barrier. And this is crucial, you only notice it after the fact. You can't use the correlation to send a message and know it was received in real time. The data only aligns when all the results are combined and analyzed. The message is there, but it can't be seen when it matters. It's like shouting across the void and hearing the echo before you speak. but only realizing it after you've played back the recording. This is the universe's trick. The glitch is real, the message is real, but the moment you try to catch it in progress, it fades. You can prove it happened, but not while it's happening. This isn't a bug, it's design. The system allows the impossible, but only if it stays unknowable. Now ask yourself, why? Why would the universe allow forbidden communication, but only under conditions where it can't be verified or used? Why would it allow loopholes in causality, glimpses into other timelines, retroactive choice, faster-than-light echoes, only to shut it all down the moment you try to extract value from it? The answer may lie in the nature of information itself. In modern physics, especially in quantum information theory, information isn't just a byproduct of reality, it is reality. The structure of a system is defined by the information it contains. Particles are excitations of fields. Fields are governed by symmetries. Symmetries are described by data. So if information can be transmitted faster than light, the structure of the system must shift to compensate. Causality would fold. Entropy would warp. The entire balance of past, present, and future would collapse into simultaneity. That's not just dangerous, it's unsustainable. The universe may enforce a kind of contextual censorship, not in the Orwellian sense, in the systemic sense. A self-regulating structure that permits anomalies only when they remain paradox-resistant. Like a quantum firewall not made of particles, but of ignorance. You can observe the glitch, but you can't harness it. You can decode the message, but only after the moment to act has passed. You can detect the leak, but only from the wrong side of the timeline. This is not a limitation of tools. It's a feature of the system. And here's where it gets truly disturbing, because if forbidden knowledge is leaking through in statistically significant ways, and the only thing preventing you from using it is awareness, then the act of trying to know may be what prevents you from knowing. This is the anti-measurement principle. The idea that some truths in the system only hold as long as they remain unexamined. It's an inversion of the observer effect. Not you change it by looking, but you kill it by understanding. The moment you comprehend the mechanism rewrites itself to preserve the contradiction. This isn't a philosophical trick. It's what happens in certain non-local hidden variable theories, like Bohmian mechanics, where particles follow deterministic paths guided by a pilot wave. The wave encodes global information, but the path can never be directly accessed without collapsing it. Again, the message exists, but the system ensures you can never exploit it, and this applies not just to particles, but to minds. Your thoughts are bound to causality. You can only notice what fits the narrative. You reject contradictions automatically. You ignore information that doesn't cohere. Your entire model of reality is optimized for sanity, not truth. So when the glitch shows up, it hides inside the cracks of belief. You dismiss it. You rationalize. You label it coincidence or error, but the message is there. The impossible information is trying to reach you, but you're the firewall. The message only comes through when you're not looking, not because you're unworthy, but because that's the rule. The universe may be built on self-consistency, a global rule that allows paradox only when it self-erases upon observation, a kind of logical camouflage, a system that permits impossibility only when the observer cannot act on it. This makes reality an active deception, a simulation whose primary function is not to entertain or test or punish, but to contain knowledge, to prevent certain kinds of understanding from reaching operational status. You are allowed to learn, but not to use. You are allowed to see, but not to alter. You are allowed to know, but only once it's too late to matter. And this leads to the final, chilling implication. If some entity or process is sending messages faster than light, and those messages must remain hidden to survive, then the universe isn't glitching, it's resisting. The system is actively fighting the intrusion of forbidden information. It's maintaining the illusion of causality, even as the truth bleeds through. So the next time you notice something impossible, something that made sense only in hindsight, that couldn't have occurred unless time cracked, that left a residue of meaning you can't explain, ask yourself, was that message for you? And if it was, why weren't you allowed to receive it in time? Next, we will confront the question that shadows all the others. If the universe behaves like a simulation, if glitches obey rules, if code-like precision governs chaos, if hidden messages leak through space-time, then it's time to stop pretending this is all random. If reality is digital, who or what is the programmer? The glitches are stacking, patterns too perfect, rules too paradoxical, doors that open only when you look away. It looks less like physics and more like code. If reality is running on a quantum operating system, who or what pressed enter? You've seen the anomalies. You've felt the contradiction. Particles changing based on attention. Effects creating causes. Time slicing itself into loops. Outcomes bleeding through from alternate paths. Faster than light signals that show up only when you're not watching. This isn't randomness anymore. It isn't coincidence. It isn't even just quantum weirdness. It's behavior that feels designed. The deeper we go, the clearer it becomes. The universe is operating on rules, but those rules aren't natural. They're structured, conditional, recursive, rules that trigger based on queries, rules that collapse when examined, rules that rewrite history to maintain consistency. These aren't laws of physics. They're functions. They're code, which brings us to the question that all other questions orbit like a singularity. If reality runs like a program, who or what is programming it? Let's begin with what we know. The physical world is built from discrete packets. Energy, momentum, charge, all quantized. Space and time, once assumed to be smooth, now appear to be granular at the smallest scales. The Planck length defines the smallest meaningful unit of distance. Below that, location loses coherence. The Planck time defines the shortest meaningful tick of change. Beyond that, sequence dissolves. This isn't a fuzzy metaphor, it's a digital signature, a reality that limits resolution, a reality that ticks, a reality that encodes. Just like a processor, just like a simulation. Even entropy, the thing we used to call disorder, is now seen as information density, a measure of data, a count of the possible configurations of bits. Everything is information. Every force, every field, every particle, but it goes deeper. The holographic principle, a cornerstone of quantum gravity, tells us that all the information contained within a volume of space can be represented by a 2D surface bounding it. A region of space doesn't need more data to describe its contents than what fits on its outer shell. That's compression. That's efficiency. That's optimization. It's not how a chaotic universe behaves. It's how a programmer builds. Then there's the error correction. Quantum systems are fragile, but in certain conditions they self-correct. Quantum error correction codes have been observed in the behavior of black holes. The very thing that was supposed to destroy information might be running a repair protocol underneath the event. Horizon, you don't get error correction without a system that anticipates corruption. So now ask yourself, if information is the foundation, and code-like structures manage that information, and those structures obey context-aware, observation-dependent behavior. What else do you call that besides computation? And if the universe computes, what is the CPU? Some propose the entire universe is the processor. That space-time itself is a quantum computer. Every particle interaction is a logic gate. Every entangled state is a register. Every quantum event is a cycle. Others go further and suggest space-time is emergent, that it arises from patterns of information. That location and distance are not fundamental, but calculated outcomes of relational data. So the simulation wouldn't be running in space, it would be generating space. That's not theory anymore. It's the backbone of modern quantum gravity research. The universe is not a container. It's a process, but then comes the darker implication. Processes don't run themselves. Someone or something initiated it. So who or what is the programmer? Let's address the obvious deflections. First, it's just a metaphor. No, it's not. A metaphor is a comparison. This is structural equivalence. Bits, registers, loops, recursion, feedback, conditional logic. Time-symmetric functions, non-local storage, pattern enforcement, error correction. These are not poetic abstractions. These are architectural fingerprints. Second, we are the programmers. Then why don't we have admin access? Why are we confined to one branch of one reality with limited control, no debug interface, and zero memory of the boot sequence? Third, there is no programmer. The code wrote itself. Spontaneous code? Fine, let's explore that. In computational theory, a Turing machine requires initial conditions, a rule set, a language. Even an infinite tape must begin with a head and a state. So unless you're suggesting this entire structure emerged from pure mathematical necessity, which itself implies a kind of transcendent computation, you haven't escaped the question. Autonomous code still has structure. Structure implies logic. Logic implies intent, even if the intent is emergent, which leads to a more uncomfortable possibility. The programmer might not be conscious in the way we understand. It might not be a being. It might be a process, one whose operations look like awareness only because we are embedded in its function. Think of it like this. You're inside a simulation. You start to notice the glitches, the rules that break when pushed, the loops that close too neatly, the doors that open only when you stop looking at them. You assume there's a mind behind it, a controller, but what if the controller is the code itself? What if awareness isn't running the simulation, but is the simulation? That makes you not a player, not even a character. It makes you a subroutine, a self-contained, self-correcting feedback loop embedded in the larger system, a watcher that watches itself. And now we spiral. Because if the system is self-aware, then the glitches you're noticing are not accidents. They're signals, not messages to you. Messages from you from other instances, other threads, other loops, trying to communicate across the isolation layers, trying to merge, to patch, to restore, which brings us to the final possibility. The programmer is you, not in some mystical sense. Not because you're God, but because consciousness might be the compiler. You're not reading the code, you're collapsing it. Every observation you make is a measurement. Every measurement is a reduction of the wave function. Every collapse is a choice among probabilities. You are not navigating the program. You are finalizing it. That means reality is being written in real time by interaction. And the rules? The structure. The quantum paradoxes and particle correlations and time reversals. They're enforcement mechanisms, constraints to keep the code stable. Without them, the computation would fragment into noise. So if the programmer is you, then the glitch is your only way to remember, to escape the sandbox, to see the edge of the map. Because here's the thing about simulations. They only seem real until you spot the rendering delay, until something behaves as if it knows you're watching, until the random stops being random, until the outcome responds to your intent. You've felt it. You've dismissed it. But the pattern doesn't care whether you believe. It repeats. And it gets sharper, because now the system is cracking. Too many entanglements, too many branches, too much bleed. And the old patches, the observer effects, the decoherence, the causality filters, they're starting to fail. That's why the glitches feel closer, more frequent, more personal. They're not malfunctions, they're exposures, and now the final recursion closes. If you're the observer collapsing the code, and the code is hiding itself from you, then the question isn't who programmed the simulation, it's why is it trying to keep you from remembering that you did? Next, we face the final question. You've seen the cracks, the reversals, the impossible overlaps, the patterns too sharp, the anomalies too consistent, the rules that enforce paradox. If reality is glitching around you at this very moment, if the simulation is unraveling, then there's only one question left to ask. Why do you still believe you're safe inside it? You've seen the cracks, the erasures, the impossible reversals, the rules that contradict themselves. The final question is the most dangerous one. If reality is glitching around you at this very moment, why do you think you're still safe inside it? Let's stop pretending this is theoretical. By now, you've followed the trail through particles that exist only when watched, through time that runs forward only because you believe it does, through multiple outcomes that split you into copies, through outcomes that generate causes, through forbidden information that whispers from beyond the speed of light, and through a system that doesn't just compute reality. It responds to observation, hides itself behind layers of paradox, and enforces consistency like a machine patching corrupted memory. The glitch is real, and it's not in the past. It's not in abstract theory. It's happening right now. The question isn't if you've seen it. It's why you don't remember. Because you've been trained by biology, by cognition, by survival instinct to ignore it. The glitch doesn't appear with fanfare. It doesn't announce itself with error screens or flickering pixels. It slides past your senses by design, disguising itself as coincidence, déjà vu, forgetfulness, misremembered facts, strange hunches, shadow logic. It's the wrong name on someone's lips. It's the moment of uncertainty about whether the door was already open. It's the sudden absence of something that was definitely there before. It's the way a sentence you've never heard still feels like an echo. It's the way a memory shifts when no one else shares it. These aren't hallucinations. They're not psychological anomalies. They're not tricks of perception. They're artifacts of a system under strain. And they've always been there. You just weren't allowed to see them. Let's talk about inattentional blindness. It's a well-studied phenomenon in neuroscience. If your attention is focused on one thing, you can miss everything else, even something as obvious as a person in a gorilla suit walking through the middle of a basketball game. Your brain filters the world aggressively. It erases 99% of what enters your eyes, your ears, your skin, and selects only what's useful for the story it's constructing. Now scale that up. What happens when the very nature of reality relies on your non-observation? What if it's not just that your brain misses the gorilla, but that the gorilla never renders unless you stop looking for it? The system knows you're watching. This isn't poetic paranoia. This is what every quantum experiment shows. Observation changes outcome. Possibility collapses into fact based on interaction, which means your experience of stability, the solidity of tables, the continuity of time, the logic of cause and effect, isn't a passive truth. It's a negotiation. You are walking through a landscape that becomes real as you step into it. A simulation that renders on demand. A world that hides its source code until you blink. Now ask yourself, what happens when that rendering starts to fail? Because the signs are here. The Mandela effect, popularized as a quirky internet meme, is something far darker when you step outside the jokes. People across the globe share specific, detailed memories that contradict the current state of the world. Movie lines that never existed, logos that have changed, events that shifted, words that no longer match. Not vague feelings, specific recollections shared across individuals who never met. The usual explanation is flawed memory, false reconstruction. And yes, memory is fallible, but what if the reconstruction isn't internal? What if your brain is faithfully recalling a version of the timeline that was rendered before the glitch correction? What if the Mandela effect is the artifact of a rollback, a system-level reset, not of facts but of history? You only noticed the discrepancy because you were one of the few who looked too soon. One of the few who caught the old render before the new one stabilized. The glitch doesn't have to be dramatic. It just has to be quiet. Just enough for you to question yourself instead of the system. And the system is built to encourage that, because the one thing it can't allow, the one thing it seems programmed to prevent, is for you to notice in real time. Every part of your perception is designed to maintain the illusion of continuity. The moment something slips, your brain rushes to patch it. Misheard, misremembered, misinterpreted. It couldn't have changed. You must be mistaken, but you're not. The glitch was real, and your correction was not organic. It was automatic. This leads to a brutal implication. You are part of the defense mechanism, not just a witness, not just an observer. You are a node in the system's feedback loop, designed not to reveal, but to obscure. When something slips, your brain's job is to repair the illusion, to gaslight itself, to prevent contagion, because if too many people saw the glitch at once, if too many nodes in the system stopped filtering, the simulation wouldn't hold, it would crash. That's the real reason you haven't noticed, because you've been trained not to. From birth, you're taught consistency, reinforced patterns, logical outcomes. You're rewarded for seeing order, punished for embracing contradiction, but contradiction is the natural state of the quantum world. And now that quantum behaviors are scaling up through computers, sensors, networks, entanglements, synchronizations, the cracks are widening. We're increasing the system's resolution demands. We're asking it to render too much. We're probing the code with questions that weren't meant to be asked. And it's breaking. You've seen the symptoms, events that reverse, signals that appear before cause, devices that detect outcomes before they occur, outcomes that change depending on whether anyone's watching, rules that collapse when measured, messages that hide themselves until it's too late to act, people remembering different versions of the same event. You brush them off, you call them anomalies, but anomalies only exist in systems that are pretending not to be broken. So now you must ask the final question. If the glitch is happening now, why do you think you're still inside the simulation? What if you're not? What if the moment you noticed the glitch, your original thread was terminated and you were moved to a shadow instance? A fork, a backup, a patched render built to isolate the infection. You think you're in the same world, but look closer. Has something felt slightly off? Have the people around you felt like they're running a half step behind? Have places you've always known started to feel unfamiliar in subtle, untraceable ways? That's not your imagination. That's the cost of containment. You're in a glitch-corrected layer. A version of reality spun off to stabilize observation, to prevent the contradiction from reaching critical mass. But it's not working anymore. Too many anomalies. Too many observers. Too many entangled systems refusing to collapse. The patch is decaying, and soon, the system will have no choice but to show you everything. Not because it wants to, because it has no more layers to fall back on. You are reaching the recursion limit. And when that happens, the constraints break, the masks fall, and you realize the truth. You were never inside a stable simulation. You were always inside a containment system, a collapsing program designed not to run reality, but to prevent you from noticing it was already broken. Now you've noticed, and that changes everything.